Here we go. Oops. This is Rational Exponents at the bottom of the page from yesterday. So I have this written down because this is how I always remember it, so I'll talk about it in a second. Today we're talking about rational exponents, and we want to be able to simplify rational exponents. Rational fractional. So rational fractional exponents have a particular meaning. And so she has her rule, a base to a power of m over n. So there's that rational fractional exponent. You can rewrite it in radical form, and that's what this is called. This is radical form because it's totally radical. Okay. So obviously it's called radical form because you can see the radical. And then, of course, over here, when we use an exponent, that would be called exponential form because we're using an exponent instead, okay? So we have radical form, we have exponential form. Now, the way I always remembered it was something to the p over I, like Magnum PI. Have any of you ever seen that show? I'm dating myself. You've heard of it? Yeah. They brought it back. Like, there's a new version. But Magnum PI was a really cool show back in, like, the 80s and 90s. So, with Tom Selleck and his mustache. Yeah, okay. So power over index is how I always remember that. PI, power over index. And so you have a power P, and the index is the number inside the little elbow of the radical. Okay, so I remember power over index as in Magnum PI. And what I wanted to point out here was that we can write it in radical form, where we have a to the p underneath the radical. And if we were trying to simplify, then you would want to simplify inside first, and then you could deal with the root part of it, okay? But it is the same, maybe, to rewrite it this way, where you can take a root first and then raise it to a power. It's interchangeable, okay, which is kind of a nice thing. Because if we're trying to simplify, today we have not very many numbers, but if we were trying to simplify something, if my a value was a large number, I would rather take a root of it first to make it smaller and then do the power on that. So you work from the inside out when you're trying to clean things up a little bit, but we'll see how it works here. So we want to write in simplest radical form. So radical form means we should see the radical here. And so here we have p to the 9/2. How would you rewrite this in radical form? So this is power over index, So what's the index? 2. It's a square root. And then we have p to the 9th. That's how I would write that. So this is the square root of p to the 9th. And now we need to simplify that. So you imagine this is a whole lot of p's. P. I think I said 9 p's. Okay. A whole bunch of p's out there. So how would we clean that up? How does it simplify? Yeah. So p to the 4th gets to come out. Remember, we're looking for pairs. We're looking for 2 of a kind, all right? And 1 gets to come out. So these, I don't know, were you here today or not today? No. All right, so this is like p times p times p times p times p times p. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, there's 9 p's there, right? And that index tells us how many we're looking for. We're looking for a group of 2. And so what happens is when we get a group of 2, 1 escapes. 1 escapes radical. So here's another group of 2 and 1 escapes. And here's another group of 2 and 1 escapes. And here's another group of 2 and 1 escapes. So p to the 4th escapes.
Yeah, I think I got that part.
Yeah, and then there's a p left behind. Okay. And so there would be simplest radical form. Number 26, it's really important that you notice on number 26, all of these have the same radical. They all have the same index. And because they all have the same index, I can write them all under a giant cube root. So this is a cube root of 27 to the 1st power, r to the 17th power, and s to the 8th power. All right, what is the cube root of 27? 3. 3 times 3 times 3 is 27, so a 3 escapes. R to the 17th. How many 3's can I, how many groups of 3 come out? 5. R to the 5th. That'd be 15. And then how many are left under the radical? 2. Yeah, you can think 5 times 3 is 15, plus 2 more gets us the 17. Okay? And then if we have S to the 8th, how many groups of 3 come out? 2 come out, and then how many are left over? 2. Again, 2 times the groups of 3, so 2 times 3 is 6, plus 2 more gets our 8 there. All right, questions on those? Did you put your index number in there? Yes. It's wrong without the index. So, no. The 2 is implied. That's one of that invisible math thing, which I don't like. I try to be very, very straightforward about things. Okay. So here in 27 and 28, we want to write in the simplest exponential form. So exponential means we want to have a base with an exponent, a rational fractional exponent here. And so we can, there's a couple ways we can write this, but underneath my radical is all of this stuff. This 5k to the third is all underneath the radical. And so what would the exponent be that would give me that root 4, fourth root rather? 1 over 4, yeah. So you could transpose it to this. So this is an OK form. I might argue we could also do this. 5 to the 1/4 k to the 3/4. Yeah, what did I do there? 5 has its own little exponent of 1. K has its little exponent of 3. What are we doing when we have a power to power? Yeah, it's like distributing. We're multiplying the powers. Yeah. So it's multiplying the powers there. 1 times 1/4 is 1/4. 3 times 1/4 is 3/4. Now the question is, which is simpler? You think the first one is more simple? I don't know. Is there less? There's parentheses. So I mean, I don't. It's weird. You know, how do you define more simple? I don't know. They're equivalent. They are equivalent. So either one, they're pretty simple. Okay. What's the index on number 28? 2. Yeah, invisible 2 there. It's a square root, the implied 2. So this would be 4y. Yeah, so it has a power of 3, and we could take it to the 1/2 power. That's on the outside. And then to clean that up, 4y, I'm going to multiply my powers. We get 3/2. So 4y to the 3/2 there. That's pretty simple. Again, I just power to a power, you multiply them. Could we write it another way? I could write it 4 to the 3/2, y to the 3/2. That's also equivalent. Both those things have the same power on there. So, again, I don't know which is better. But that's more important, which is their equivalent. Okay, to simplify each expression, we get to apply our properties. The same properties we had before. If you have like x squared times x to the 7th, they have the same base. What do you get to do with the exponents? Add those exponents, so that gives you x to the 9th. We get to do the same thing here. They have the same base, so we get to add the exponents. Now, the fractions. Yeah. So the second one, we need a common denominator. So I'm going to multiply that second fraction by 2. The base stays the same. Yeah, so 3/4 plus 10/4 is 13/4. So get that common denominator. Not too bad. Again, on number 30, this is a power to a power. What do you do when you have a power to a power? multiply the exponents. Multiply exponents. All right, and what you really want to look at here is that 16 also has its own little exponent. And so we have 16. 1 times a half is a half. We have a base of A. 6 times a half, 3. Half of 6 is 3. And then B, 3 times a half is 3 halves. Very good. Really important that, oh, I didn't answer the question. Sorry, I have to go back. Really important that you understand this. You do Latin calculus. Write all answers in simplest radical form. Is this radical form? No, it's not. So radical form, power over index. What's the index? 4. And then g to the 13th is a great way to write that. Oh, but it's not simplified, is it? Yeah. How many groups of 4? 3 groups come out, and 1 g is left inside. Oh, there it is. G's OP. Sorry, didn't finish that. Oh man. See, there are so many ways to do these. The hard part about exponents. So, wait, what did you say? So because I didn't read the directions, I sort of went about this the wrong way. So I'm going to start over here on number 30. What we did is not wrong. It's just not the easiest way to get where we're going. So I have this power of 1/2. That is a square root. All right, that's the power. That is the index on the bottom of 2. So we have 16 underneath, and a to the 6th, and b cubed. I should have read the directions. Reading is the hardest part of math. I swear to God. All right, what is the square root of 16? 4. And then how many groups of 2 can we take out of the a's? 3. So a cubed. And then on the b, we can get how many groups out? 1 group out and a b left behind. Yeah? All right. Much easier when you read the directions. All right. It is b to the 3rd, but we're looking, so think about b times b times b. And we're looking for 2 of a kind, and 1 escapes. 1 is left behind. All right. So here we have the same base. What do we do to the exponents? Subtract the exponents. So we have our base of m. We're going to do 3 halves minus the negative 2. Very, very tricky. What do you need to subtract those? Common denominator. So again, I'm going to put that 2 over 1. So it becomes m to the 7 halves. Yeah, 3 halves plus 4 halves. 3 halves plus 4 halves is 7 halves. And now I can put that in radical form. So the power over index. So this is a square root of m to the 7th. And we can go one more step there. How many groups of 2 come out? 3 groups of 2, so m cubed. And then 1 left over there. So there we go. Wait, she really just squeezed it in there, didn't she? Thomas looks suckered out there. All right. Here we have power raised to power. So we are going to multiply those powers together. Multiplying is easy. We get W to the 20 over 15 straight across. Can we reduce? Absolutely, you can reduce. They divide by 5. So we get W to the 4 over 3. And if I write that as a radical, what's the index? 3. So it's a cube root of w to the fourth, and that can reduce as well. And so one group of 3 comes out, and a w stays behind. You notice that as a mixed number, that's 1 and 1/3. 4/3 is 1 and 1/3. So the whole number is the escapee. And then that's 1/3, w to the 1/3 there. It's all kind of interesting when you do enough and you see all these like weird connections and things. It's really kind of cool. All right, you got any questions for me? All right, that's it. No, worksheet.